So, as always, if you've got specific questions about the exam, you're more than welcome to come by my office and talk about them. More than happy to go over things. Answer key is on Moodle. All those good things. So, what we're going to be talking about is building on the concepts of probability that we talked about in those first couple of chapters, or first several sections. But what we're going to do now is set up some what they call frequently used distributions. And what we're going to be concentrating on is the development of these distributions and looking at when we see a type of problem, how are we going to know what distribution to use? Okay. So the first one is a fairly straightforward distribution. It's what's referred to as the discrete uniform distribution. Oh, and by the way, this is also where we're going to start memorizing all these things at the front cover of your book. So the discrete uniform distribution is the bottom one that's on that left-hand side of the inside cover of your book. So in this particular one, your sample space is the set 1, 2, 3, up to n. And the reason why it's called the uniform distribution is because each of these elements in the set are equally likely to occur. So the probability is uniformly distributed over each possibility. So if that's the case, if each number here is equally likely to be chosen, what's going to be your PDF or your PMF here? No matter what you plug in for x, what do you get out for the probability? Well, you've got n things to choose from, and you're choosing one of them. So what's the probability you're going to choose? Yeah. It'd be 1 over n, right? That's how it's going to be equally likely. So this would be our discrete uniform distribution. That's the PMF for the discrete uniform distribution. What we're interested in here, of course, with these distributions is not just the probabilities, but things like their expected value and their variance. So let's see if we can calculate that. Or their mean and their variance, either way. So for the mean here, how do we calculate the mean again? The expected value, what do we do? Yeah, Justin. Okay, so it's the sum of x times f of x for all x in the sample space, right? And in this case, what's our sample space? 1 through n. And our f of x is 1 over n. All right, so as far as the sum is concerned, what's changing? The x is changing, right? So that 1 over n is just a constant. What can I do with the constant? Put it up front, right? And do we have a formula for, this is the sum of the first n integers? N positive, do we have a formula for that? N times n plus 1 over 2. So you'll get the 1 over n pulled out in front, multiply it by n times n plus 1 over 2, and then your n's, of course, will cancel, and you'll just get n plus 1 over 2. Does that make sense? We're talking about expected value, talking about average. Does that make sense? That would be the expected value. Well, think about a classical discrete uniform distribution. Roll a die, record the result. Do it over and over and over again. Right? Because each of your sides should be equally likely. If I roll a die over and over and over and over and over and over and over again, I should get 3.5 for an average. Right? Half the time it should be something 1 through 3, half the time it should be something 4 through 6. Pardon me. Remember the idea of expected value is weighted average. Well, the weights are here are all the same. So all we're really doing is just averaging these numbers, right? Well, halfway between 1 and n is n plus 1 over 2. Halfway between 2 and n minus 1 is n plus 1 over 2. So this makes sense if that would be the expected value. All right, to get variance, remember we need to calculate our expected value of x squared first. Remember also this is called our second moment. Remember these are when we have expected value of x to a power. Those are moments. So the expected value is the first moment. This is we're calculating the second moment. We can do third and fourth and so on moments if we'd like. So same idea. This is the sum of x squared times f of x for everything in the sample space. So this is set up just like, pardon me, goodness. This is set up just like the previous. Except that we've got an x squared instead of an x. Again, the 1 over n is a constant, and we have a formula for doing the x squared, some of the x squareds, some of the squares of the first n positive integers. Do we know what that formula is? Close. I agree it's over 6. I agree there's an n plus 1. I agree there's an n. Almost. There's a 2 in it. It's 2n plus 1, yeah. Then again here, your n's go away, and you have n plus 1 times 2n plus 1 over 6. Is that the variance, by the way? Did we just calculate the variance? No, what did I calculated the second moment, right? Not the variance. How do we get the variance? Good. Yep, right. Second moment minus the square of the first moment. Expected value of x squared minus expected value of x quantity squared. So we've got n plus 1 times 2n plus 1 over 6 minus, this will be n plus 1 squared over 4. Get a common denominator of 12 here, right? Multiply the first one by 2 and the second one by 3. So if we FOIL out the first one, I get 2n squared, but I'm going to multiply it by 2 because I'm getting a common denominator, so I'll have 4n squared. I get 3n when I FOIL times a 2, so I'll get a plus 6n. I get a plus 1, but again times a 2. Everybody understand why I'm multiplying that by 2 while I'm foiling in the common denominator? And then minus, I got to do the same thing over here, but I got to multiply by 3. So we'll get minus 3n squared minus 6n minus 3. And notice that your 6n's cancel. We're left with just an n squared minus 1 over 12. So this is the kind of stuff that we'll be collecting for these particular discrete distributions, calculating their means, calculating their variances. We're also going to be doing something called the moment generating function on these, and we'll talk about what we mean about that when we get to that particular section. Pardon me. Let's see if we can do a problem with one of these with one of these discrete uniform distributions, and it'll throw in a little twist. Let's look at number 1 on that problem set 6 that I handed out. right, so you've got two discrete uniform distributions. One of them is on the set 1 to n, and the other one's on the set from 0 to n instead. It asks you to find the variance of x minus the variance of y. Well, we know what the variance of y is, right? We just calculated it, didn't we? Okay. So we know that the variance of y here is n squared minus 1 over 12. Now, we could do the exact same thing that we just did, deriving the formula here for expected value and variance on the set for x. It looks like a different set of numbers. Why not rederive it? It's not hard. We could do it. It didn't take us that long to do it in the first place, right? Okay. It's more work than you have to do, though. Okay? Because being uniform on the set from 0 to n is almost like being uniform on the set 1 to n plus 1. Right? It's just been shifted down 1, isn't it? Right? So being uniform on the set from 0 to n is just like being uniform on set from 1 to n plus 1, just being shifted. Now we talked about this before the test. If I shift the distribution, does it change the variance? No. It'll change the expected value, obviously, right? If I take everything and subtract 5 from it, I would expect the expected value to be shifted by 5, right? But if I shift it, it doesn't change the variance. Variance is a measure of spread. All I do is pick up a data set, pick up a distribution, and move it. I didn't spread it out anymore, right? The only way it gets more spread out is if I multiply it by something, stretch it or shrink it. Okay? So the variance of x, in this case, should just be n plus 1 squared minus 1 over 12. And again, for the reason for this is because x is essentially uniform on the set 1 to n plus 1 and shifted down 1. And I'm going to put shifted down 1 in quotes because I have an intuitive understanding of that and I don't want to write a whole bunch of we subtracted 1 from each individual thing. All right, we just took the data set and subtracted 1. Does that make sense? So that n in the variance formula is basically just counting how many things are in there, as long as they're all spaced 1 apart. Okay? This has to be spaced 1 apart for this to do it. If they were spaced half apart, the variance would get changed because it's not spread as much, right? In fact, if they were all half apart, that would be 1/4 of the variance. Because remember that constant on the inside in the variance will end up getting squared when we do expected value of x squared. We had problems like that before. So now we can answer the question. This is just going to be, so variance of x minus variance of y will just be the difference of these two things. Which gives us what? 2n plus 1 over 12? Questions on that one? Yeah, Grace. Sure.
When you were deriving the formula, you had the n times n plus 1 times 2n plus 1.
Yes.
What is that 2n plus
It's in the formula.
So like if it was another one, would it be 3n plus 1?
No, it's a different formula. Sum of the x cubes is n times n plus 1 over 2 all squared.
And the 6 is just.
No, it just comes up. Yeah. For the discrete uniform, yes. Yeah. We're going to change the distribution here. It depends on, remember your f of x depends on the distribution. For discrete uniform, it's always going to be 1 over n, the number of things in the sample space. Other questions on this one? All right. So the first big one that we're going to talk about, this is actually section 2.4 in your text, is the binomial distribution. And as a piece of the binomial distribution, we have what are referred to as Bernoulli trials. So the best way to think about, at least for me, the best way to think about Bernoulli trials is that you've got an experiment that you're going to run, and there are only 2 possible outcomes. Either you succeed or you fail. There's no gray area. Okay? So I flip a coin, I get heads, I get tails. Pick whichever one you want to call a success. Okay? That's an example of a Bernoulli trial. I flip a coin, heads or tails. It's the only possibility. Okay? But I can apply it to other situations too. Okay? I roll a die, I get a 3 or I don't get a 3. Like 3 or not 3. If you're a casino goer or a craps player, I get 7 or I don't get 7. Roulette player lands on red or doesn't land on red. Okay. But you can apply it for all sorts of different situations. 40% of the population is a registered Democrat. 35% of the population is a registered Republican. Something along those lines. So you can talk about, if I go sample a bunch of people, what's the probability I have this many Democrats or this many Republicans? So in that case, with a Democrat, it's either Democrat or not Democrat. Republican or not Republican. Okay? So you can think about these, as long as you can divide it into 2 groups, success and failure, that's the idea of a Bernoulli trial. Okay? So just to write that down, a Bernoulli experiment or Bernoulli trial, they're essentially the same thing. Is, again, a random experiment. So like flipping a coin, rolling a die, watching a roulette wheel spin around and the ball land in a slot. So it's a random experiment, selecting a person in the population at random that has 2 mutually exclusive outcomes. And we usually call them success and failure. Don't take those words literally. It's just the words that are typically used. Sometimes when you're looking at success, you're looking at counting the number of deaths. And I don't think anybody considers death a success. Okay. What's that? You've completed life. Congratulations. So that's just the words they use to denote these different things. All right. So for a single Bernoulli trial, now most of the problems we're going to be interested in are consecutive Bernoulli trials, and that's where we're going to get the binomial distribution from. But for a single Bernoulli trial, I keep putting the I in the wrong spot. For a single Bernoulli trial, the PMF is f of x equals p to the x 1 minus p to the 1 minus x, where x is 0 and 1. Let me tell you about what the different pieces are. P is your probability of success. In this case, we're associating the number 1 with a success. So that would be the probability that x equals 1, and you can check if I plug in 1 into that formula, I really do get p, right? Well, if your probability of success is p, and you have mutually exclusive outcomes, what does the probability of failure have to be? It has to be 1 minus p, right? Because the probabilities have to add up to 1, correct? So 1 minus p is your probability of failure. Or the probability that x equals 0. So we're going to put the number 0 in for failure. So what we've really defined here, and I didn't write it out at the beginning, but what we've really defined here is a Bernoulli, what's referred to as a Bernoulli random variable. Remember, random variables are functions that talk about the outcome of your experiment and associate numbers to them. We talked about that before the test, right? So I think of, like I said, the classic Bernoulli trial is flip a coin, heads or tails, right? The classic Bernoulli trial. Well, heads, tails isn't a number, right? Those are qualitative aspects. So what that random variable again does is it changes those qualities to quantities. So if I want heads to be success, then I would say heads is 1. If I want tails to be failure, then tails is 0. The Bernoulli random variables always have outcome 0, 1. Okay? All right. It's not too hard here to calculate what your expected value and variance has to be. I'm just going to write it down. For a Bernoulli random variable, the expected let me call it, give it a name, let me call it x. The expected value of x is p, and the variance of x is p times 1 minus p. It's really not hard to figure these out because you have to sum up 2 things, right? One of which is going to be multiplied by 0. Right? When I do the expected value of x or expected value of x squared, I'll plug in 0 for x for one of the 2 choices. Right? So again, for both of those, I have to sum up 2 things, one of which is 0. It's not very interesting. Not very hard. Okay? So we can do that. All right. So this is just basically what the Bernoulli random variable does is it gives us the basic foundation to build up what's referred to as the binomial distribution. So let's talk about that for a minute or two. All right. So when we get the binomial random distribution, this distribution comes up from conducting a sequence of independent and identical Bernoulli trials. So you flip a coin over and over and over and over and over. You roll a die over and over and over and over and over. You take a sample from a large population. That's a little dicey. It's an approximation of this. If you're taking a sample of 1,000 and there's 2 billion people in the population, or 2 billion things in the population, it might as well have just had an infinite number of things that as far as statistically significant goes. Okay. So, but it's conducting a sequence of independent, so one thing doesn't rely on the other. When I flip a coin, the next coin flip didn't depend on the first one. When I roll a die, the next roll of the die did not depend on the previous one, or any of the previous ones. Identical means that you're doing the exact same thing over and over and over again. Okay? What we count, the number of successes in n trials. We actually call this whole process a binomial experiment. I flip a coin 15 times, I count the number of heads. I roll a die 75 times, I count the number of threes. I take a sample of 150 people, I count the number of registered Democrats. I pull light bulbs off an assembly line. Say I pull 1,000 light bulbs off the assembly line, I see how many of them are defective. That's what we mean by calculating the number of successes in n trials. All right. So let's see if we can figure out what the distribution is. So we're going to let x be the number of successes in n trials. Well, if there are x successes in n trials, how many failures are there? N minus x, right? And this is the whole being a Bernoulli trial, right? If I didn't succeed, I failed. Right? There's no good try. Okay? If I didn't succeed, I failed. Okay? So if x of the time I succeeded, the other n minus x of the time I failed. Make sense? Okay? All right. So that's the Bernoulli trial aspect. They're identical, so I'm calculating that the probability of success does not change from trial to trial. That's identical trials. That's important. The other important part is independent. When we have independent events, how do we calculate the probability? If I want the probability of both happening at the same time and they're independent, how do we calculate it? What do we do? Multiply, right? So if I have x successes and n minus x failures, we can calculate the probabilities then by doing x successes. So I would have p to the x and 1 minus p to the n minus x. So we would have x successes and n failures. However, the way I kind of said that is I haven't taken into account when these things happen, right? So for example, if I had if I flipped the coin 5 times and was looking at the number of heads, say I want to know the probability that I got 3 heads. Well, it could be 1, 2, 3 that I got the head, right? Or it could be 2, 4, 5, right? Or 1, 3, 5. There's different possibilities, correct? As a matter of fact, from those 5 positions, I want to choose exactly 3 of them to place the heads. How do I count that? 5 choose 3, right? So in this case, in front of this, we would get an n choose x. So this will be your PMF for a binomial distribution. So again, just the different pieces, what they mean, just to go through it again. Ignore the n minus x for the time being. Okay? P to the x, there's x successes, they're all independent. So I find the probability that they all happen by multiplying them all together. But that's not the only thing that happened. So if we had x successes, we had n minus x failures. We find the probability by multiplying them all together. Right? This is just one big, long and probability using independence. Right? This n choose x in front is just counting the number of ways that many successes could happen. Right? I've got x places for, excuse me, try that again. I've got n places for x successes to happen. Once I place the successes, the failures have to fill in the gap. That's why there's got another product. Once I place all the successes, the failures have to go everywhere else. So this is your PMF for a binomial distribution. Now we'll do expected value and variance here in a minute. But just to show where this works at, let's look at the other packet that I handed out that actually, shockingly enough, is titled Binomial Distribution at the top. Let's look at 19.1. "30% of all electrical fuses fail to meet building standards. We're taking a random sample of 10 fuses. What's the probability that exactly 3 will fail?" Okay. All right, so we have a random sample of 10 fuses. We're told that 30% are going to fail to meet standards. Since we're doing a random sample, our selection of one fuse shouldn't affect the selection of any other fuse, right? So they should be independent and identical in that case, at least as best as we can approximate. Okay? So that's what makes this a binomial experiment. So what is going to be our P in this case, do you think? What are we trying to count? What constitutes success here? Failure to meet standard, right? That's why I said you have to be a little bit careful with the language, right? What's constituting a success here is failing to meet standards. Okay? So what is our P then? It's the 0.3, right? Because it says 30% fail to meet standards. Right? So if we want the probability that x is equal to 3, exactly 3 failed to meet standard. Oh, by the way, what else do I need to know? I need to know n. 10, that's the number of trials, right? That's the number of fuses we're selecting. We want, in 10 fuses, what's the probability that exactly 3 are defective or fail? So what's this going to look like? Okay. Good. So it's just plugging it directly into the formula, right? The n was 10, the x is 3, so we get 10 choose 3, 0.3 to the third, 0.7 to the seventh. I think it was answer B. All right. You okay with that? Do we know? I mean, just plugging the numbers in shouldn't be a challenge. But do we understand why we used this formula? What was it? What was it about the problem that was telling us that we were using this formula? Because that's what we're going to have to determine as we're reading these problems as we go through. It's a matter of being able to pick the distribution. So what was it about this particular problem that was telling us that we wanted binomial distribution? So the things that tell you that it's binomial distribution is you're doing repeated trials of the same thing, right? Are we doing repeated trials of the same thing? Yeah. Is your probability to stay the same throughout the repeated trials? Yeah. It's always going to be 30%. I know it's a little, you can argue with me that there's a finite number of fuses, so it changes slightly. All right, so they're all the same. You're selecting fuses over and over and over again, right? Probability doesn't change from fuse to fuse. And the independence part that's being chosen at random. That's telling you you've got a binomial experiment. So we use the binomial distribution. Okay. Again, we're going to be learning lots and lots of different distributions as we go through the next couple of chapters. It's going to be very regimented, I believe, as we go through. I'm going to read this problem. I see to use this distribution. I try to use that distribution. But we still have to be able to read it carefully to figure out what distribution we're using. So think about these things as we're going along. All right. Let's see if we can calculate the expected value and the variance, the mean and the variance for binomial distribution, although you should be able to guess. At least for the expected value, you should be able to guess, right? If I roll a die, what's your problem? And I say you wanted to count the number of threes that pop up as you roll it over and over and over and over again. But what's the probability of rolling a 3? 1/6. So if I roll a die over and over and over and over again, what fraction of the time would you expect that 3 to come up? 1/6, right? So if I roll the die 36 times, how many 3s would you expect? 6. I would take the 36 times the 1/6, right? Take the number of trials and multiply by the probability. If something happens 20% of the time and you do it 100 times, you expect 20 of them to come out, right? So as far as expected value goes, we should know that the answer is number of trials times probability. It should be n times p. Let's see if we can do that. So let's say we want to do the expected value So our expected value formula again is you take x and multiply it by the PMF, right? Our sum here in this case will go from 0 to n, because if I run n trials, I could have no successes, I was very, very unlucky and didn't succeed at all, or I was very, very lucky and succeeded all n times, right? Agree? Okay. All right, what do we get when we put in 0 for x? No matter what else happens, what do we get when we put in 0 for x? 0, because of this part right here, right? So I might as well change this to the sum from x equals 1 to n, because when I plug in 0, I get 0. Now I'm going to rewrite my n choose x using the formula. That's n factorial over x factorial times n minus x factorial. I can cancel that x in front with 1 on the bottom. If I cancel the x out front with 1 on the bottom, what's left on the bottom where I canceled the x? X minus 1 factorial, right? There's an x that starts off this factorial, and the next one down is x minus 1, right? So when we cancel this x with that, we get x minus 1 factorial. Oops, I said x minus 1 factorial and didn't write it. Okay, that doesn't look pretty so far. So we got to be a little bit clever, because it's what we do, try to be clever. All right, well, notice back up when we started this, I said that this was a PMF. One of our, I'll scroll back down a minute, I know somebody made that, get it all written down. But one of the fundamental things of a PMF is that if I sum this up over the entire sample space, I should get what? 1, right? You agree? The sum of this would go from 0 to the number of trials, right? Okay. Right now I've got a sum that starts at 1. So what I'm going to do is I'm going to re-index it by, instead of going from 1 to n, I'm going to go from 0 to n minus 1, and I'm just going to change the letter from an x to a k. So notice that your k here is x minus 1, right? I shifted everything down 1, so the k is x minus 1. So we'll get n factorial on top, k factorial, n minus k minus 1 factorial, p to the k minus 1, 1 minus p to the n minus k minus 1. K plus 1 is x. So I can think about putting in k plus 1 everywhere I see x. Okay. All right, so still doesn't look like binomial, but I did change the sum to start at 0, right? To make this look like a binomial experiment now, this should be your number of trials, correct? N minus 1 should be your number of trials, so instead of n factorial, I should have an n minus 1 factorial here, right? And this is number of successes, so instead of a k minus 1 here, it should be k plus 1. I plugged in the wrong thing. It should be k plus 1, because k plus 1 is x, so I should get a k plus 1 there. So instead of this being k plus 1, it should just be a k. So what we're going to do is we're going to take an n out in front, take a p out in front, leaves us with this big fraction. And I'm going to rearrange the exponent in that last one to n minus 1 minus a k. Oops, and I forgot my factorial. All right, so ignore the np out in front. My sum goes from 0 to n minus 1, so that fits a binomial distribution pattern, right? Look at this formula here. This is n minus 1, and then it's k, and then it's n minus 1 minus k. This is our formula for n choose k, right? That's exactly what that is, isn't it? This piece right here, or n minus 1 choose k, I should say. That's n minus 1 choose k. Do I have my number of trials matched up where it needs to be? Sum goes from 0 to n minus 1, n minus 1 choose k, and then I got the 1 minus p to the n minus 1 minus k. So this part that we have over here in our summand, so just to write this down, the summand here is the PMF of a binomial random variable with n trials, n minus 1 trials, and probability of success of still p. So the summand is a PMF, and I'm summing it up over all the possibilities. So what does that sum have to equal? Well, it has to be 1. So what do I get for a final answer? NP. And before we did all of this extra work, isn't that exactly what we said we expected to happen? If P is your percentage, your probability of success, and you do something n times P would be the percentage of successes you would expect. It's a lot of work to get what you would expect to have happen, right? But it verifies that your intuition is correct, right? Intuitively, we would think that if I succeed 20% of the time, and I do it 100 times, I should succeed 20 times. That's what that formula says, right? If you're an 80% free throw shooter and you shoot 100 free throws, you'd expect to make 80 free throws, right? That's what that expected value means. Okay. Does it happen all the time? No, but that's what the expected value is. Right. We'll do more of this Wednesday, as well as talk about the hypergeometric distribution. That'll be the next one we start talking about. So have a good one. We'll see you then.